Hello, everyone. So, this lecture is about alkyl halides in the continuation of our next chapter we have started. But today we are covering a very important topic, and that is the regioselective, which seems to be challenging and complex most of the CAM students. But in this lecture, I assure you that if you pay attention and you watch the lecture and practice that one, so regioselectivity is no more a complex concept for you. So you'll be able to predict the major and minor products whenever the alkanes are going through the halogenation. So, before discussing that, how we can predict and how mathematically we can calculate what the major product will be in one particular reaction. So, the first thing is that how we can define and what is regioselectivity actually. So, the first thing is we will define the regioselectivity. But before the definition, I will continue from the example. As in the previous lecture, you were supposed to prepare the haloalkanes, and we see how we can prepare haloalkanes from the alkanes through the bromination, through the chlorination. So if you just focus on this example, this is the propane, which is your starting material, and this undergoes to the bromination reaction in the presence of heat or light, which is the reaction medium to facilitate that reaction, because in the darkness and without heat, that reaction is not possible, because these are not the alkenes one, they are the alkenes, the saturated one. So there is some kind of energy is required to break one of the CH bond, and then that hydrogen will be replaced with the bromine or the chlorine, whatever the halogen we are treating with the alkanes one. So now if we just look at this example, so this bromination product, there could be the two possibilities. So if you work on it and you practice, and you can just see and try to draw the structures and to assign the IUPAC name to these ones, so you will conclude it that there are the two possible products when we treat the propane with the bromine. So the one product is the 1-bromopropane, and the other one is the 2-bromopropane. Why it's so? Because if you just look at the both terminal sides, the two the ending sides of this propane one. So these both protons are both sides of this carbon are the primary one, and they have the primary hydrogens, while the central carbon is the secondary carbon, and the hydrogens which are attached to that carbon are the secondary hydrogens, right? So if we replace any of the hydrogen from this side, because both are in the single bond to the carbon, so they have the free rotation, free spatial rotation, so that is the same one. This is not the chiral one. So if you replace any of the hydrogen from this methyl or any of this one, so you will get the product 1-bromopropane. While if you replace any of the hydrogen among these two hydrogens which are attached to the central carbon, so that will result in 2-bromopropane. So if I hope you have the concept about the secondary, primary, and the tertiary carbon, though I have touched that concept here. But if you need more detail about that one, and you want to refresh your concept, so you can just check out my lecture on the reactions of the alkanes on YouTube. So here I have explained more in detail that what are the secondary, tertiary, and the primary carbons are. So now you can see the percentages I have written, I have mentioned here. So this 2-bromopropane is the 92%, and this product appear as 8% of the total percentage of the product. Now the percentages which I have quoted in that example, these are the experimental one, that when we set up the reaction of the propane with the bromine in the presence of light and heat, so what we got in the reaction flask, what were our products? So we got the two kind of products. So one was the major and one was the minor. So major is which is in higher yield on the percentage, and the minor one which is in a low yield. So we got these two products. Now the question is this one, that how we can predict and what is that thing which is holding and which is affecting, which is regulating that uh, that happening, that we should have one product as a major and one as a less. Do we always get the mixture of the product in the halogenation of the alkenes one, or there are some kind of reactions where we get only the one kind of product? So if we get the mixture of the products, so are they in the different percentages, or we get the 50-50, or maybe the major difference in the percentages one, right? So that all things we questions we will address in this lecture, in this topic. So now moving forward, so basically this example was to give you the to build your concept that there is a factor, there is something which is ruling and which is managing this, that the bromine has to be it has to selective for one of the carbon, and it has some kind of preference, right, over the other product. So the thing is what that preference termed. So that preference is basically the regioselectivity, which we are going to discuss and to explore what actually the regioselectivity. But as a general concept, the regioselectivity is basically a selectivity or a preference of an atom to bound to one atom over another one, right? And the explanation of a reaction's regioselectivity, or if the reaction is not a regioselective reaction, this discussed under the regiochemistry. So if I say that you have to discuss the regiochemistry of that reaction, it means I'm asking you about that either you can comment on this one, that this reaction is following some of the preference pattern. Is this a regioselective or is this not a regioselective, right? So the common example is the Markovnikov addition in regioselective reactions. So we know when the alkenes are in reaction with the halogen one, so there is the addition reaction. So addition is either following the Markovnikov rule or not following the Markovnikov rule, and that depends on the reaction conditions. So generally when we treat alkenes with the halogen, so what happens that the hydro, if for example we are treating any of the alkene which HBr, which is the any of the halogen acid. So hydrogen will bound to that carbon or that side. It will added it on that side where there are already higher number of the hydrogen, and the bromine, which is a bulky and the halogen group, so that will attach to that side which is already deficient as compared to that side of the hydrogen. So it means then this kind of pattern, if that kind of product is formed through the addition reaction, so this is called Markovnikov's addition, because this is following the Markovnikov rule, right? In this slide you can see the airplane. So there is objective for showing that picture. So to give you the daily example and a concept that what that preference of the selectivity means, if you are have the good concept about the selectivity and the preference, you know that enzymes are very specific and certain kind of reactions are very selective. But for the general understanding is this one, that if you have to move from one city to another city, so you have the certain possibilities and the certain routes to adopt to move from one city to another one. Either you can choose by road, either you can choose by air. So if you're choosing airplane, to travel to the airplane or by air, you want to travel by air. So that is certain type of preference, and of course that preference is on the basis of some factors or some of the objectives, right? So that preference of the compounds in organic chemistry of an atom to be bond to a certain position, so that is basically the regioselectivity. Now we will discuss the example. Again, I'm referring the same example so that you are not just switching and confused with examples. So we will keep that same example to illustrate and to discuss all aspects of what is happening and how we can discuss that this reaction's regio chemistry, right? So the propane reacting with bromine and the presence of heat or light. So we got two kinds of products. That is straightforward because wherever there is a hydrogen, so there is a possibility to replace with the bromine. There are the two bromopropane and the one bromopropane plus HBr, which is the second part of the bromine, right? And that is removing by replacing the one hydrogen from the alkane. And there is the hydrogen bromide, which is liberating from the reaction. Now, the thing is this one, that in alkane, if you just focus on firstly on the propane, right? So how many total protons we have in propane? So there are basically 8 protons in the propane structure. Now, if we categorize and we see that how many primary, secondary, or the tertiary protons are there, so we see that there are the 2 protons out of 8 are the secondary one, and the 6 protons out of 8 total protons, these are the primary one, right? So in this table, the first thing is the prediction based on the ratio of 6 primary protons and the 2 secondary protons, that what is our general perception about that this reaction should happen in a way that there should be the 70% chances for the formation of one bromopropane, and there should be the 25% chances for the formation of two bromopropane, just on the basis the availability of the primary and the secondary protons in the propane, right? But what we experience experimentally, that when that reaction has actually happened in a lab, so we um, got only 8% of the one bromopropane in the 92% of two bromopropane. Now that is the bizarre thing, that if we just look at the structure of that compound, so there are the 6 protons which are primary, so there should be the 6 times more chances, 6 opportunities for that replacement of with the bromine. So but why this is happening? So the thing is this one, that what had the fact, firstly I will just mention what the fact has established by this experimental reaction is that in the bromination of propane, the substitution of a secondary hydrogen rather than a primary hydrogen is strongly favored. So the 2-bromopropane is a major product and the reaction is highly regioselective, right? Uh, highly regioselectivity is termed when there is the huge difference between the minor and the major product, right? We will see another example with the chlorine where where this is not too regioselective as the bromine is, right? So what is I will discuss that why this primary and secondary protons do matter, right? So one thing we have established that in case of the bromination, if we have the primary, secondary, or the tertiary one, so the bromine has the greater preference and the selectivity for the tertiary, then secondary, and then the primary one, right? So if you have to quote the percentage of the product, so that is on the basis of that regioselectivity, not on the basis of whatever the total number of protons, whatever the number of primary protons are available. So then this is the range or the difference in the prediction on the basis of the number of protons, and this is the actual value, actual percentage on the basis of the regioselectivity. Now moving to the next slide, where I have quoted the two examples. One case is with the bromine and other case is with the chlorine one. Now, the previously we did the bromination of the propane, and now this is the chlorination of the propane, the same reaction conditions. And you can see, of course, there are again the two possibilities, the two chloropropane and the one chloropropane, right? Now you will observe that in bromination, that difference was quite huge, and that is highly regioselective, right? Because there we were getting the 92% versus 8%, and here we are having the 57% versus 43%, right? So we will see why this difference is in between the bromine and the chlorine. Both are the halogen, both are belong to the same halogen group, electronegative. So what are the different factors which are determining that one, right? So here comes the preference and the selectivity, which is more selective, right? If you just compare the above example, that is the 2-methyl pentane with the bromine, heat or light. And here you can see, if you just focus on a structure, so in the structure, we have the primary. So let me write this one, so that will be easier for you if you still have any confusion. So here you can see this is the primary carbon, and of course the hydrogens which are attached to that primary carbon. So that is the termed as the primary hydrogen, right? This is the primary. I'm writing 1 degree. That is the notation we use for writing the primary, secondary, or the tertiary one, right? So 1 degree is for the primary, and here you can see this is the secondary one, and this is again the secondary one. And now another thing which we haven't see in the previous example. So here, this is the tertiary carbon, right? So now we have a structure with the primary, secondary, and the tertiary hydrogens. So the bromine as the highly regioselective, right? So in this particular reaction, whenever in an alkane we have the tertiary carbon and the tertiary hydrogens, so bromine is having the explicit and exclusive preference for the tertiary one. So we are not getting the mixture of the product, we are straightforwardly getting the single major product as a 2-bromo 2-methyl pentane, right? And that is the major, right? Or you can call this above the 99% is that product, right? So this is the fraction of the HBr which is removing the second part, right? So here you can see, compare now, so that concept will be developed right now. I hope you have at the phase that you can infer the chlorine is less regioselective as compared to the bromine, but again chlorine is also a regioselective, right? So here we will see that why that difference is happening. So the factors which are controlling the regioselectivity, or which is influencing, which are affecting the regioselectivity, are majorly, they are the two components to understand. So one thing is the reactivity of RH system. This RH refers to carbon and hydrogen when we're talking about the organic compounds, right? And the reactivity of X dot radical, right? So this unpaired electron is to mention that this halogen in a radical form. So RH, the strength of RH varies slightly depending on whether the proton is primary, secondary, or tertiary. The following table shows the bond dissociation energy, that is energy required to break the bond in a homolytic fashion, generating R radical and H radical. And you know what the homolytic cleavage is. So I will further refer you to see reaction mechanism of the alkanes and in my previous lecture. So you will have the difference between the homolytic and heterolytic cleavage, right? So homolytic means when the bond is breaking in a way that the both contributing atoms are getting the equal share. So here, if you just look at this table, so you will see that this is a case where this is the methane, right? And the bond dissociation energy for breaking this carbon and hydrogen bond is 435 kilojoule per mole. When we have the primary structure, this is the primary carbon and its bond with that hydrogen. If we eliminate one of or break one bond of that one, so then it requires 410, less than the methane one, right? And the next case is a secondary one. And here the energy bond dissociation, the BD energy is again dropping, right? For the tertiary one, we have the 380. So if you just look at in the kilocalories per mole, so again, the trend is the same one. So only the values and the units are different. So what we found here, so basically what is happening when we are moving from the methane to the tertiary carbon alkanes, so the bond dissociation energy of the carbon and hydrogen is reducing. It means that bond is easier to break as compared to the secondary, then the primary, and the methane one. The reason is this one, that if you just compare this extreme case, which is a tertiary one, so if I draw it in a more open version, so you will be able to see, right? Now I'm not concerned with the valency. I just wanted to show that what is happening with this one, right? So this carbon is the tertiary one, and this is bonded with the 3-methyl, right? And I'm just writing it as R groups, right? So when that bond cleaved, right? So this is happening that there is the either the carbocation, right? Or we will see then what is happening, right? If this is the heterolytic level, so there will be the carbocation and then there is the hydrogen, right? So A91. But this is happening through the radical mechanism. So there is the one unpaired electron and there is the one unpaired electron, right? So this carbon is stabilized from these three sides with three R groups, right? So this is some kind of the species or the moiety which can sustain in a system for a longer time as compared to this small and tiny methane, which is not as stable. There is no stabilizing units which can keep it intact in the system for a while. So this is very reactive. So it cannot survive in the system, right? So if you just compare the methane versus the tertiary structure, so the best example to see the difference is that if there is the 1 year uh, kid and there is the 4 or 5 year kid in a mall, so he's more dependent to their parent attention and who is able to walk around in a mall. So definitely that is very small, that's tiny, that is reactive, fragile. So this is just not sustaining a system, while this is somehow can manage itself. So that's why this radical, which is forming the tertiary radical, is more stable. So it means that bond is easier to break. While when the radical is not stable, so that bond it is not willing to cleave that bond easily. So that's why we are having the differences in the bond dissociation energies for these ones. Now the next factor is the halogen radical, X dot. So this is the bromine radicals are less reactive than the chlorine radical. What does it mean? Means the bromine radicals are the less reactive towards the abstraction of the proton as compared to the chlorine one. Bromine says to be more selective in its reaction and preference to react with the weaker RH bonds. Because this is the less reactive means it's comparatively stable to sustain in a system, so it can just look into the preference and what will give it the more stabilized form. The more reactive chlorine radical is less discriminating in what it reacts with, so this is not as bothering as the bromine is, that bromine only look for the tertiary if available, otherwise it will go for the high preference for the secondary, and then on a least preference with the primary one, while the chlorine is the more reactive one, so it can react with the primary, secondary, and the tertiary one without the major discrimination, right? So this is the least discriminating about the primary, or the, you can say, the least concern as compared to the bromine about the tertiary, secondary, and the primary one. Now, the thing is that we can predict the major products from the halogenation of the alkanes. Now, the one major thing which you need to note and to keep in your mind is this one. The equation I'm referring to you and the mathematical prediction about the major product is that we have to limitize ourselves only to the monohalogenated products. So this equation is only valid, or you can say the limitation of this is that it is only applicable for the cases when we have the monohalogenation, when we have the di-tri halogenated products. So that is not, we can't predict well. We cannot predict the major products by this equation, right? So for the monohalogenation, we will see that how we can predict and how we can calculate mathematically that that is the major product, and that one, and another one is the minor product. So before discussing that equation, the major thing which I want you to mention is, and you have to remember that um, reactivity factor, the regioselectivity values for the bromine and chlorine is that for the primary, bromine has the preference R1, chlorine has 1, right? While for the secondary, bromine has 80 times more preference than the primary one, while chlorine has 4 times mm, preference for the secondary over the primary one. While in case of tertiary, and you can see that huge difference in case of the bromine as compared to the chlorine. So bromine has a 1600 times preference for the tertiary one. So that's why in the previous example you have seen, whenever there was a tertiary carbon or the proton was available, so then it was the only major product we obtained through that reaction, right? So this equation is this is the expression of that equation, that how you can calculate that one. So the percent pi is basically the yield of product. You wanted to check the certain product, that what percentage that you will obtain through the certain reaction. Now the NHI is the number of hydrogens available for that position where you are supposed, or you are looking for that product, right? Ri is the regioselectivity value of bromine or chlorine. So then you have to check that either that reaction is with bromine, or you are looking for a chlorination reaction. So you will put that value for the protons. For example, if the product percentage you are looking for is for some kind of primary hydrogen, so you will write the on that position, if this is the same position which is giving you the same IUPAC name, and that is a site, so then you will write the total number of that protons available. That could be the 3, that could be the 2, right? and then multiplying it with the regioselectivity value for that proton. If this is primary, you will multiply with that one. If that is a product with the secondary proton, so you will quote that one. If there is a tertiary, you will quote that value, right? Now, in the denumerator, what is there? So this is a sum of the total all kind of protons multiplied by their regioselectivity value. So if you just still a little bit open that one, I will show you in the next mathematical example that how we will do that well, how we can conduct that calculation. So this is the overall expression that what you need for calculating or predicting the major product in the monohalogenation of the alkanes one. So here this is an example that we are treating the 2-methyl propane with the bromine in the presence of lighter heat, and we are only looking for the monobromoalkanes, right, plus HBr. As I have given you the one of the task when I just limitize yourself that you have to see draw the structures and to name the products which are the monohalogenated from the given alkanes in the preparation of the haloalkanes, right? So this is the 2-methyl propane, and we are treating with the bromine. So what is happening here? The first choice or the first possibility for the product is that we get the 2-bromo 2-methyl propane, right? And this is the with this tertiary proton, right, where the bromine will attach, and the rest of these 3 sites are the equivalent ones. So these are the methyl one, CH3, CH3, and CH3. So whatever the side hydrogen is replaced with the bromine, so if you will name this one, so this will give you the same product, right? And that is the 1-bromo 2-methyl propane. So another trick is this one, another clarity you have to keep in your mind, that you can't go for the side chain, but if this is giving you the same IUPAC name, so you can't quote it as a different product, right? If this is giving you the same IUPAC name, it means these sides are equal in one, and that is the same compound, the same product, right? So you will just write the two uh, the possible products which are having the different IUPAC names. So here in this case, we are having only 2 kinds of products, 2-bromo 2-methyl propane and the 1-bromo 2-methyl propane. Now we wanted to calculate the prediction, we want to predict the percentage of the product, one of the product, this is a 2-bromo 2-methyl propane, right? So how we are going to do that one? So using the same equation expression. So what I told you that firstly you will see that for what product you will you wanted to calculate the percentage. So this is a 2-bromo 2-methyl propane, and that is the structure of this one, right? It means in the numerator, firstly you will write that proton which has replaced with the bromine, right? So this tertiary carbon has only 1 proton. So there, or in other word, there is only 1 tertiary proton. So we write 1 here. Multiplying it with the 1600, which was the regioselectivity value for the tertiary proton for bromine, right? Now in denumerator, we have to write the sum of all of the protons available for that structure with their regioselectivity value. So in this structure, we have 1 tertiary proton, and we will multiply it with its regioselectivity value, that is 1600, plus, because we are taking the sum of all of the protons with their regioselectivity value. So in total, there are the 9 primary protons. So 9 multiplied by 1. 1 is the regioselectivity value for the primary proton for bromine, and that is same for the chlorine and the bromine one, right? Now multiplying the whole of that figures with the 100 to get the percentage of this product. So what would be your answer? So you just have to code that one. So that is the 94%, right? And this is all about the regioselectivity, what its concept, what are the factors which are influencing that regioselectivity, and we have seen how we can predict the percentage of the product when the alkanes is subject to the chlorination or the bromination, and we are getting the monohalogenated products, right? At last but not least, there is a point that why we are only focusing on the chlorine and the bromine. The reason is this one, that the fluorine from the halogen is too reactive, too exothermic, that this is out of control reaction. So this is not easy to control in a lab in a normal conditions, right? While the iodine is the least reactive. So the most of the halogen and the haloalkanes, so we are focusing only on the chlorine and the bromine for their reactivity and the ease of the reaction. So at last, there is a task for you, and I hope you will just get the interest for that task. So the task is hexane has 5 possible isomers. So I'm referring these the constitutional isomers, which are just have the changes in the branching and their connectivity, right? So these are the alkanes, and they are the 5 possible isomers of the hexane. So you have to draw and calculate the regioselectivity of monochlorides of two of isomeric forms, hexane and 2,2-dimethylbutane. So I have picked the 2 isomers of the hexanes, and you have to react it with the chlorine and prepare all possible monochlorides of this hexane and the 2,2-dimethylbutane, and you have to calculate the percentage of these monochlorinated products from this one, and do submit it on a Moodle. And who are not a registered students, you can comment and below the video. So I would be happy to suggest and to comment that either you are at the with the right answer or not. So thank you. That's for today. Have a good day.